All right, so this week we are moving on to Module 4, and so we're going to start off with the playing with compound interest, and so that's going to take us a couple of sections to get that going into next week. And last week, y'all took your exam, and I'm still grading those. I'm almost done. So you'll know if yours is graded when you go to the exam page. Well, your exam grade probably went up. And when you go to the exam page, it'll say view, so I think it says view scored assessment. And then you'll see my comments under certain problems. I didn't comment on every problem, but I commented on some of them, especially if something went wrong. And so I think I've graded 80% of them so far. I got one or two more to finish grading this afternoon. So take a look at that. Most people's grades went up by about 20 points after I reviewed your work. So thank you for submitting work on those. All right, and hopefully the prep went well. We're gonna pick up with a problem we left off last week. And so today it's gonna be similar to other days. I am going to give some examples of what we're doing in the lesson. And it's important you pay attention and take some notes on the problems I'm going to do here, because that's going to make answering some of the questions on the lessons easier, because there's some tough questions on this particular lesson. So the big ideas that we're looking at here are this idea of using repeated multiplication for certain problems. And those repeated multiplications end up leading to exponents. So that's the big idea of the day. We're going to play with some financial data. So this idea of a certificate of deposit annual percentage rates, we're going to start exploring that today. And then some ideas about when interest is collected, daily, quarterly, monthly. Let's see who else just joined us. We got Brennan, welcome. Brenda, Alex, glad you could join us. All right, so let's get some notes going here. So we're now in Module 4. And whereas in Module 3, the big idea was about rates of change and the idea of slope, in this Module 4, we're going to be moving on to some more complicated expressions, mainly the ideas of exponential. So it's a little bit different than linear change. And so we're just going to go over some examples. The first one we're going to look at in sections 4.1 and 4.2, the idea of where compound interest comes from. And so I'm going to set that up with a situation, then we'll play around with it on a spreadsheet, which is an awesome place to look at how compound interest comes from. And the big idea about compound interest, welcome Cody, is that compound interest just really comes from simple interest, which we've already looked at, and I'm going to remind you of that. So the idea of simple interest, we came up with a formula before for that, and the interest amount, I, is some starting amount, P, times some rate, times some amount of time. So we have our interest amount here. And we get that interest amount by taking some starting investment, usually called the principal or present value. And then we multiply that principal by a rate. And often that's an annual percentage rate. And then by some amount of time that goes by. So this is my I equals PRT. And the idea of an annual percentage rate is important because whenever I have an annual percentage rate, then the time here has to be in years. So this is an idea we played around with couple weeks ago, last week. We're going to extend it a little bit to turn into compound interest. And a lot of times when interest is calculated like this, it's called a dividend. And when you reinvest that dividend, that's when compound interest starts to happen. So we're gonna take a look at that. So what I want to do is I just want to look at a simple example where we have an annual percentage rate, APR. And let's use a nice easy number like 2. 2%, remember percent literally means divide by 100, and 2 divided by 100 in slang is 0.02, but if you read that properly, you read it by the decimal place. So these are my tenths, these are my hundredths, so this is properly read as 200ths. So that's my APR. Let's invest $1,000. And if we let T equal 1 year, then the simple interest is just that $1,000, just my 1, times the percentage as a decimal, unless you have a special button on your calculator, times the amount of time that's gone by. So 2 out of 100, check on your calculator, should be 20 out of 1,000, so that should be $20. Now, 2 things can happen to this if we made an investment. At the end of the year, they send me 20 bucks, say, hey, thanks for the $1,000 investment, here's your interest of $20 for this year. Or maybe they keep it in my account. So this would be after 1 year, after the first year. I started off with P equals $1,000, right? I just gained an interest amount of $20. And so altogether, if I add those 2 up, if I tell them to keep the money in my account, I now have $1,020 in my account instead of just $1,000. So I just put that back in. So if I put all of this together, right, how I calculate that interest amount, then what I have here is my new amount right here. That's just the P plus the I. The I, remember, came from taking P times R times T. So altogether, this 1,020 right there is P plus the PRT. And in the last unit, I said we could perform a little mathematical magic on this called factoring to simplify it a little bit. Does anybody remember what we can do to the P here, how we can rewrite this to simplify it?
Would it just be 2P?
Not quite. So in this example, like if I get rid of the RT for a second, I could write it a little bit simpler. So in this example, we've got P plus the 0.02 here, and then if T is just 1 year, I'll have P times 0.02 times 1. 0.02 times 1 is just 0.02. And often we write that on the other side. So you could say I have 1 P and I have 0.02 Ps. So altogether, I should have 1.02 Ps. And I can kind of generalize that here by saying another way to look at it is I just factored this P out and wrote it once. So if I try to do the same thing here, what I get is I pull the P out. What does that leave behind? Well, right here, there's really 1 P, so I'm left a 1 there. I took this P out too, right? I took both of those out, so that leaves just the RT. And if you compare this 1.02, that 1.02 is the 1 plus RT, right? Because R is 0.02 and T is 1. 1 times 0.02 is 0.02. 1 plus 0.02 is 1.02. So my point is that this right here is the same as that right there, that 1.02. And I have to make that observation that this common P can be pulled out there. So this is a useful formula. New page. So for simple interest, looking at a future total, for any time period, the future total is going to be the principal plus the interest, and the interest is always PRT. So that's one way I can write my future total. But because we have this idea of factoring now, another way I can write it as P times parentheses 1 plus RT. So the blue formula and the green formula make exactly the same calculation, it's just written a little bit different. These two things are the same, they are equal. But we're going to find that this version is going to be much more useful. I'll show you why now. So this is a super important version of simple interest added back on. All right, so we know how to calculate simple interest and add it back on. So what we're going to do is we're going to look at what happens over a whole bunch of years to my future amount. And I'm going to put a year 0 in here just to indicate I'm starting with $1,000. And then I want to look at what happens 1 year later, what happens 2 years later, what happens 3 years later, and then we're going to hope to extend this to some kind of general formula, like where we do like an N. But I'm going to call it just T down here. And we already did the calculation for 1 year. That was the $1,000 plus the $20, which gave us $1,020 total. And just a reminder of how we calculated that, that was 1,000 plus 1,000 times the 0.02 times the 1, right? That's the calculation we made a minute ago, a page back. That's where this 1,020 came from. Now, the key difference about the second year is instead of starting with $1,000 for the second year, I now have 1,020 to work with. So basically, I'm going to repeat this calculation, but with the 1,020. So at the end of the second year, I'm starting with $1,020, and then I'm adding on interest. How do I calculate the interest? Well, that's whatever my balance is times the interest rate times the amount of time. All right, and notice again, that's pretty much the same procedure I applied up here. Take whatever your balance is, find your interest for that balance, and then add it up. So we can whip that out on a calculator, and I just want to demonstrate on a calculator. So right now I've written this first way, but we're also going to try it this way and see if we get the same amount. So we're going to test that on the calculator. So whip out a calculator. If you don't already have one, you're going to need it. So we're going to compare P plus PRT. For the current year, that's 1,020 plus 1,020 times 0.02 times 1. Versus this other way, which says just take the 1,020, put a parentheses, and then do 1 plus 0.02 times 1. And what we should find is the result should be identical. Get a calculator out. I'm going to use, I think I'll use Desmos today. Calculator. So first version, 1,020 plus 1,020. And on any modern calculator, you should be able to just type all this in at once. No need to do it in stages. And this is an important skill. So I get that at the end of the second year, there should be $1,040.40. Did anyone else get that?
I did.
Okay.
Me too.
Awesome, you guys rock. Now the other version of the calculation said take the 1,020, multiply by parentheses 1 plus 0.02 times 1. And that should be exactly the same amount. Now, I mentioned earlier that this can be cleaned up inside right there because multiplying by 1 doesn't change much. So I could say this is just 1020 times 1.02, right? There's my 1, there's my 0.02. Notice I get exactly the same amount there. All right, let's put that in our notes. Okay, so this did work. The number we calculated here, $1,040.40, matches the number we calculated here. And we're going to find that this version is going to be more useful as we move ahead. So let's get back to our table here. So this right here is equal to $1,040.40. So that's my new amount. So I get a new amount here, my next new amount here, and the shortcut for that right there I'm going to write was $1,020 times 1.02. And up here, the shortcut for that is 1,000 times 1.02. Okay, that's what we just established with our calculator. Let's do year 3. For year 3 here, starting off with $1,040.40 that's been sitting in the account, a year has gone by, so we get to make the interest calculation again. So that means take whatever your balance is and multiply that 0.02 times 1. And multiplying by 1 is kind of boring. I could not write it and I'd still get the same answer, but I don't want to put it in there. That right there should be exactly the same as this shortcut right there. The shortcut says take $1,040.40 and just multiply it by 1.02. So what I'd like you to do on your calculator right now is confirm that this long version of simple interest matches this short version of simple interest. So whip those out on your calculator, convince yourself, yep, they match, or maybe they don't. If they don't, we got a problem, but they should match. So make sure. Key to being successful in this class and others like it is being good at using your own calculator. So does the green calculation match the red calculation? Try to catch up on you, catch up on the calculator with you. So first version, 1040.4 plus 1040.4 times 0.02. I get $1,061.21 if I round versus 1040.4 times 1.02 is the other version, and I get exactly the same number. And generally, we're going to round those, although on a spreadsheet, it keeps track of all those fractions of a change for us. So we'll do a spreadsheet soon. Probably halfway through class, I'll do this on a spreadsheet. All right, questions on either of these calculations here?
I have a question about spreadsheets, actually.
Yep.
So how does that, you can basically plug in like any equation and it'll solve it kind of thing?
No.
Like if you have...
Spreadsheets don't solve equations, but they can make any calculation you want.
Okay, yeah, that's kind of what I meant, I
Yeah,
guess.
so-
If you
so
have
we
the
can-
information.
So what we can do, what we'll do in a little bit is on the spreadsheet, instead of going to our calculator one at a time for these, we'll just tell the spreadsheet how to do it once and then to do that automatic fill, and it'll do it all the time for us.
Oh, okay.
Yeah, so we'll do that shortly. All right, so let's see, what was the amount we got here? 1,061.21, is that right? Yeah, let's write that in the notes. So we believe this is equal to $1,061.21. Now, if we weren't putting, now notice we're putting the interest amount back in. Once we start putting it back in, not only is our original 1,000 collecting interest, but our interest is now collecting interest. And this is the part that's called compound interest. If I were to just do simple interest on 3 years, I'm not going to get the same amount here. So, oops, I need a new page. Let's go here. So if I just did straight simple interest for 3 years, interest, the interest amount, I, would just be whatever you started with at $1,000 times your interest rate. Mine was 2%, so as a decimal, it's 2/100ths, times the amount of years that go by. Well, I already know that 2% of 1,000 is 20. 20 times 3 is 60. So with just straight simple interest, I would only get $60 at the end of 3 years, if nothing happened in between. But here we're saying every year, oops, where'd it go? Back here. Every year, instead of just taking the interest out, let's leave it in and see what happens. And you can see, look, I'm a little better off than $60 here. I get an extra $1.21. Now, another thing to note, if I pick on this number right here for a second, where did the 1,040 come from? Well, that came from multiplying the 1,020 times 1.02. So I'm just going to break that down for a second. So I've got 1,040 times 1.02. That's where this number came from. But this number right here came from taking the 1,020 times 1.02. And I still have this 1.02 hanging out there. Where did the 1,020 come from? Well, it came from taking 1,000 times 1.02. So this part right here was 1,000 times 1.02. And then I still have those other 1.02s hanging out. So my claim is that if on a calculator right now, I took 1,000 times 1.02 times 1.02 times 1.02, I'd still get this $1,061.21. So I'm going to verify that. I'm not making this stuff up. So if I take my $1,000, after 1 year, I get to multiply by 1.02. After 2 years, I get to multiply by 1.02. And then after 3 years, I get to multiply by 1.02. And look at what it comes out to. Exactly that 161.02. My point is, back into the notes here. Right here. That this version of the formula is going to be way more useful because it lets me get my work done in way less steps calculator-wise. Now, hopefully you guys know the answer to this. If I repeatedly multiply by something, like I am right here, is there a shortcut mathematically for writing that down? So I don't have to keep writing 1.02 over and over again. What's the shortcut there?
Can you use exponents?
Yeah, totally. So instead of writing that 1.02 3 times, I just say, well, just take the 1.02 and raise it to the 3rd power. Now, the cool thing about that is if somebody says, okay, well, what happened in the 10th year? All I have to do is put a 10 up there because that 3 is because I'm in the 3rd year. So let's just double check that on a calculator, make sure that it indeed works. I broke my calculator. There you go. 1,000 times 1.02 raised to the power 3. Calculator says, oh yeah, 1,061.21 to the nearest cent. So we have developed this nice shortcut. So I'm just going to redraw my table for a sec. Push the right button. That button. So it turns out our shortcut that we've developed here, based on how many years have gone by and are calculating our future amount. Skip up to 10 years or just call it T years. Initially, I have $1,000. 1 year later, it was 1,000 times 1.02. 2 years later, it's whatever 1,000 times 1.02 squared is. 3 years later, it's 1,000 times 1.02 to the 3rd power. 4 years later would be 1,000 times 1.02 to the fourth. So recognizing that I can squeeze the initial amount and the interest together, and that becomes this multiplier. So a note on some terminology, the 0.02, right, that is my annual percentage rate. Okay. It's also known as a growth rate. Right? My money is growing, and this is the rate of its growth right there. When we put it together with a 1 like that, so 1.02, this is what's called a growth multiplier. And it's that repeated multiplication by the same number that lets us use an exponent. So it turns out, like in general, like a spreadsheet version of this formula is what I'm getting at here. At least one version of a spreadsheet. There's lots of different ways to do it. It would be just 1,000 times 1.02 to the power t for time. And if somebody changes that rate on me right there, that's no big deal. I can easily change that. So if they said it's 3%, I put a 3 here. They say it's 10%, then I would have 10% here. So in general, for yearly interest, the future amount is always the principal or present amount times 1 plus your rate to the power however many years went by. So the only things I want to emphasize here, that's the same P we've been talking about. This R right here would have to be the APR, and this T right here would have to be years gone by. So the first part of the lesson is just working our way up to this formula so you can have a similar situation that you're playing with. But then we want to extend it, because although some banks pay out interest yearly, other banks, every month you get interest on your account. So we got to figure out, how does this change if we use months instead of years? And it changes just a little bit, but that's the second stage. So let's stop here.